Hi, everyone, and hello. Welcome to this session on word problems based on rates and work and interest. Uh, in our previous sessions, what we have looked at is how to tackle the statements in a word problem. Specifically, there were a few word problems that required us to deliberate on rates. So today, we're going to be looking at how rates are supposed to be dealt with, what sort of problems involve work and interest. Okay, so I hope you all can see me, and you all can see my screen and you hear me. And with this, we're going to start. So the first thing is, sorry. Okay. So the first thing is how what do these quantities represent? So in terms of representation, the core formulas for rates and work are the same. They are ratios, much like the slope was in our earlier examples, where we saw that the slope was actually something like rise over run. So what we did was we've tried to calculate how much a line has risen over how much it has traveled along the x-axis. So this was the basis of slope. And in principle, the rate is the same. The rate is, it tells us that what is the amount of work done or the quantity vis-a-vis when you have time on the gives us the rate. So in essence, the rate is the same as slope. The only thing being the x-axis now represents time specifically, whereas the y-axis could be any other quantity. So rate is your quantity divided by time, or quantity over time. Or in some cases, it's also mentioned in different terms. We're going to look at those when we look at those other word problems. Okay, and then if we are to find out, from a given rate what the time is, what we do is we kind of manipulate this specific representation. So, for example, if your rate is equal to the quantity over time, this would imply that if we take time to this side and bring rate over here, then time would be quantity over the rate itself. And similarly, if you were supposed to find out the quantity itself, you're simply going to take the time to this side. So time times r is going to give us the quantity. So if we kind of remember what the rate signifies, which is the total amount of work done, or the quantity, or the change in quantity corresponding to the time, we can find out either the quantity itself or the time itself, depending upon what sort of situation is presented to us. Okay, so and then combined rate. So we've already seen the first three bullet points. So what happens if you're giving rates of more than one elements or more than one entities? So the combined rate is always the sum of individual rates itself. Okay, so if you are supposed to find out what the combined rate of multiple contributors is, whether they are contributing to work or whether they are contributing to, for example, it's a very common topic in GRE is to as for example, inlets. There's a reservoir and some inlets are allowing some liquid, let's say water, to flow into the reservoir, and there are multiple inlets. And so what we might be given is that this is the input rate or the inlet rate of the first inlet. You've got the rate of flow from the second inlet, and then we are supposed to find out how quickly the reservoir is going to be filled up. So in those cases, or in similar cases where you've given multiple rates, so the combined work rate is going to be the sum of individual rates. Okay, so in certain cases, some rates might be contributing to the overall job, whereas other rates might be working against the completion. So for example, in a certain situation, there is a reservoir where we have multiple inlets, and then there are outlets as well. And so a question might be posed to you that if these inlets are, open simultaneously and the outlet is also open, so how much longer is it going to take for the reservoir to be filled up completely, or at what point of time the reservoir is going to be filled up completely? So these different sorts of scenarios are posed to you, particularly when rates or where rates are concerned. In almost all of the cases, the questions related to the rates are posed in terms of word problems. Okay, so we're going to look at a few of them today. We're going to start with some of the very basic problems so we know exactly how to handle different quantities in terms of rates and how to do the manipulation. Okay, right. Okay, so here's the first example. This is an example of a paper mill, which states that a paper mill requires 40 pounds of pulp to produce 10 reams of paper. Okay, so at the same rate, how many reams can be produced from 120 pounds of pulp? Okay, so um, this is kind of telling. So you don't see specifically for example, the element of time over here, but you do see the dependence of the reams of paper on the total weight of the pulp available. Okay, so this is kind of like something like this. So for example, what we are supposed to find out is how many reams can be produced from 120 pounds of pulp. Okay, so first of all, what is the first thing? So the first thing is how many reams are produced per pound of pulp. Okay, so first of all, let's look at the units themselves. We've got the reams, which is the reams of paper, over the pounds of pulp. Okay, so this is the basic unit that we are going to be working on. Okay, so for every 40, okay, so it's given over here, so I'm just going to make this symbol. So for every 40 pounds of pulp, we get 10 reams of paper. So this is what the first statement tells us, that that paper mill produces 40 pounds of pulp to produce 10 reams of paper. So for every 40 pounds, we get 10 reams of paper. So this tells us that you get 1 ream of paper for every 4 pound. Okay, so if we simply simplify this, so for every 4 pounds, of pulp, you get 1 ream of paper. Okay, and now what we're supposed to answer is at the same rate. So if this rate is consistently followed, so at the same rate, how many reams can be produced from 120 pounds of pulp? So now we're given that we're getting 1 ream of paper from 4 pounds of pulp. Okay, so this is 1 over 4. So this is your reams. Units, why I'm writing units is because units play a very important role when you're dealing with rates. Okay, and then, yeah, absolutely, thank you very much. So with over 40 pounds, okay, and what our answer is supposed to be, your answer is supposed to be in reams, right? Why? Because you're supposed to answer this question, how many reams can be produced? Okay, so here we have, say, this element. So if I multiply this with the given weight, so what's going to happen is that these units are going to get canceled out, and what I'm going to be left with is only these units, and my answer is going to be in these units. So this kind of confirms to me that the quantity I'm supposed to multiply this rate is something in weight. Okay, this weight. I'm supposed to multiply this element, reams over pounds, with weight, and that is going to leave only reams. Okay, so that is why writing the units at times becomes very important when you're dealing with rates. So again, you get 1 ream of paper for every 4 pounds, time I'm going to write this again. Time, what is the other quantity that we're given? We're given that the total amount of pulp that we have is 120 pounds of pulp. Okay, so if we do this 120 pounds, okay, so first of all, this pounds is going to cancel these out. So the units are going to cancel out. And now we're going to be left with only this unit, which is reams. Okay, so which is consistent with what we need at the answer. Okay, great. And then if we simplify this, so this is 4 times 30, this is 120. So we get 30 reams. Okay, so you multiply the constants now. Okay, so 1 times 30, and this is the unit that stays consistent. So you get 30 reams. Right? So why I'm starting with this particular example is, even though this does not have time, but this kind of represents the importance or significance of writing the units or understanding what is the significance of units. So for example, if I had, this was, let's say, I'm just going to change it slightly. Okay, if I had a different understanding of this, so what I mean is, so for example, instead of creating the original fraction as, instead of doing this as 10 over 40, so 10 reams over 40 pounds, what if we did this in the reverse order? We said that, okay, for every 10 reams, we need 40 pounds of pulp. Okay, and so if this was our formulation in the beginning, so here's the thing, if we did the same measure, okay, so we have now pounds, okay, over 1 ream times 120 pounds, and do we get the answer in reams? No, we do not get the answer in reams, because over here the reams is in denominator, so you cannot get the answer in reams. And so this initial formulation, okay, or this initial formulation, so this tells us that there's a problem with this initial formulation. And what indicates this? It is the placement of these units. So if we don't use the units initially, so there are times where we might get confused with the rates themselves, or what sort of formulation we're supposed to build. Okay, so that is why in the beginning, when you're practicing, it is essentially important that you keep on writing these units and you understand that what is the quantity that is being asked for. So you have to know that these units, if you start canceling these units out, so the only thing that should remain is the units that you're supposed to provide the answer for. Okay, all right. Moving on. Okay, so here's the kind of the a rates question, but let me first of all do something a bit more simplistic. Okay, we're going to start with this. The example states that a cyclist covers 90 miles in 3 hours. Okay, and what we're supposed to answer is that what is his or her average speed. Okay, so what we're given is the total distance which the cyclist covers, which is 90 miles, and the total time in which the distance is covered. Okay, and what we're supposed to find out is the average speed. Now, speed essentially is a rate itself. Okay, but what is speed? Speed, okay, great. Okay, speed is the distance you travel, okay, over the time it takes for you to travel that distance. Okay, so essentially, speed is a rate, because as per our original definition, the rate was any quantity divided by time. So in this particular case, your quantity is the distance, and you're dividing that by the total time it takes to cover that distance, and that gives us the speed. Okay, so now what we are supposed to provide is the average speed. And so what is the average going to be? The average is going to be, the total. I'm going to just write it down over here. The average speed is going to be the total distance over the total time. Okay. So why am I emphasizing on this word average over here is that, for example, it is absolutely possible for the cyclist, let's say these divisions represent each hour, okay? So for example, the cyclist could have done 25 miles in the first hour, okay, 45 miles in the next hour, okay, which is 70, and then 20 miles in the last hour, okay? And that cyclist would still have covered 90 miles in the total of 3 hours, okay? So this particular fact is not violated. The cyclist still covers 90 miles in 3 hours. Okay, so this particular fact is not violated in this, or you can change it to anything. So, for example, it could be, say, 40, 40, or 10. Okay, and this cyclist still covers 90 miles in 3 hours. Okay, what we're seeing over here is that the speed that they have maintained in the first half, in the first hour, is 40 miles. In the second hour, they have done again 40 miles. And in the last hour, they have done 10 miles. Okay. So their speed varies. Okay. And that is why it's important to see what is being asked. Okay. What is being asked of us over here is the average speed. And this is what makes the difference over here. Okay. So the average speed is going to be defined as your total distance over the total time. Okay. So for example, if the question was formulated slightly differently. So if the question stated, what could have been a possible speed for the first hour? Okay. Any of these speeds is possible. So for example, if for the first hour, the cyclist covered 20 miles in the next hour, in the next 2 hours, they could easily cover, let's say, the remaining 70 miles. We don't know. Okay. But it is possible. Okay, it is possible. And so all of these values are valid entries. So if, for example, I would have given you another option and said that, okay, if, you know, if you have another option which says that the average speed for the first hour was 100 miles, okay? Is this a valid option? Now, this would have been an invalid option because that would have meant that the cyclist covered 90 miles in less than an hour, whereas the statement shows that the cyclist has covered 90 miles in 3 hours. So this cannot be the speed for first hour, okay? And that is why, as I said, it is important that this connotation of what the average speed is asking of us is considered. Okay, so now for the average speed, the formula is the total distance over total time. So for example, the average rate is the same. So that would be the total quantity, any quantity, over the total time it has taken or it takes to perform this sort of activity or this sort of work. Okay. So in this particular case, what we have is the total distance is, again, coming back to our question. Okay. So the total distance is 90 miles per hour. Sorry, this is not miles per hour, but this is only the miles. Okay. So this is miles. And the total time is 3 hours. Okay. And if I do that, if I simplify this, so this is the average speed comes out as 30 miles per hour. So again, see the significance of the units over here. Okay, the units tell me that this is miles per hour, and my result is going to be in miles per hour. And the speed again is distance over time. So if I had flipped the quantities somehow, if I had, for example, reversed the fraction somehow, then my speed would have been coming in, for example, hour over miles, okay, which is not a valid unit for speed because I'm supposed to answer for speed, okay. This is again why writing down the units is important, okay. They help us verify our answers and let us know that we are moving in the right direction. Okay, so in this particular case, uh, does somebody have a question? All right, okay. So with this, we get the average speed of 30 miles per hour, which is again, uh, your answer C. Okay. So for all of these questions, again, one thing is valid, which is what we have done or what we have seen in our earlier word problems is back solving. Okay, you can always do, back solving. If, for example, in a certain situation, um, you know, um, it's difficult to make sense of the rate itself. What you can always do is understand that this is, your average rate, or this is your average quantity, and if you multiply this with, for example, these are all the rates, right? Because this is the speed, and if you multiply these rates with the time, you should get this quantity. Okay, so you can always do this with back solving as well. So for example, if the numbers were in decimals and you were supposed to find out the closest rate, okay, you could start with any one of those entries, take them, multiply with time, and see if it is the closest that you get to the total quantity. Okay, and so back solving, the principles of back solving, as we have discussed earlier in during our word problem sessions, they are perfectly valid for solving these questions as well. Okay, right. Moving on, let me just quickly do that. Okay, a lot of the word problems involve changing units. This is in fact very common, and so let's look at one example that's going to require us to do the same. A car travels at 60 kilometers per hour. What is the speed in meters per second? Okay, so now we have the rate, which is the speed, and the speed is given as, in kilometers per hour, is given as 60, I'm just going to write km per 1 hour. Okay, so the car is moving as in 60 kilometers per hour. And now what we're supposed to do is we're supposed to convert the speed into meters per second. So what we're going to do is we're going to take a look at these quantities individually, okay, and we're going to perform the individual conversion of these quantities. Okay, so we understand that the kilo in the kilometers represents 1000. Okay, this prefix kilo represents 1000. Okay, so in order to convert kilometers to meters, we're simply going to multiply this with 1000, and that is going to remove this suffix kilo, and we are going to be only left with meters because we've already written what that prefix represents, which is 1000. And then for each hour, we have, how many seconds do we have in each hour? Okay, so in each hour you've got 60 minutes, right? And then for each minute you've got 60 seconds. Okay, so this is seconds. So if I simply, for example, if I stopped over here, that would give me a unit of minutes. Okay, so that would be meters per minutes, and that is why I have to multiply this with another 60, because for each minute I get 60 seconds, and that is what is going to bring the second unit, which is minutes, right? Okay, so with this multiplication, right, now we have 60 into 1000 over 3600. Okay, and so when we simplify, so this is 600 over 36, and now we get 100 over 6, and so this is 16. So the closest answer, so this is some decimal. Okay, so yeah, exactly, we're going to get the answer in some decimal, so probably 16.67, or if you round that off, that's going to become 16.7. Okay, 16.7, again the units, meters per second. Okay, but the answers over here are provided as integers. Okay, so what we're going to do is we're going to find out the nearest integer to that, which is option D. Okay, and so option D is going to be the nearest integer to the exact answer, which is 16.7. And so now we're going to select 16. And what is the, again, we have checked for the units. So the units over here that we have calculated is in meters per second. Okay, so I hope that this is clear. So sometimes For example, you can do the reverse order as well. So in any unit conversion, what we have to understand is that when we're going from a larger unit to a smaller one, we always, you know, multiply. Okay. But when we are going from a smaller unit to a larger unit, then you have to divide. So for example, let's say I'm just going to change this question a bit. If I have a car moving at, let's say, 20 meters per second, okay? And the question asks, what is its speed in meters per minute? Okay. So now what is being essentially asked of you is to convert this unit into a different unit. Okay. The distance unit is not changing. We're supposed to provide the answer in meters per minute. And how are we going to do that? So first of all, we write this 20 meters over 1 minute. Sorry, this is second. So 20 meters in 1 second. Okay. And now, how do we go from second to a minute? Let's take 5 seconds and think, if you were supposed to go from, seconds to a minute, how would we do that? What does a second represent for a single minute? Okay. So the second, 1 second in terms of minute is, yeah, exactly. So this is, in terms of fraction, this is 1 over 60. So if there were 60 seconds, okay, 1 second represents actually, if there are 60 seconds in a minute, 1 second actually represents, a unit division in those 60 seconds, okay? So 1 second, when we're supposed to write that, as a minute, so there's a simpler way to do that as well. So you simply write 1 minute is equal to 60 seconds, right? Here's where, the units come in handy as well. So what we want to find out is, we want to define the second in 1 second in terms of a minute. So what we do is we divide both of these sides with 60. So I'm going to write this slightly more, clearly. We've got 1 minute is equal to 60 seconds. And we want the answer to represent what 1 second is, okay? So here what we do is we divide both sides of this equation with 60, okay? So we divide 60 and we divide with 60 over here. So over here we get 1. And so 1 second is now equal to 1 by 60 of a minute, right? And so this tells us that if we were supposed to convert this, what we can do is simply replace 1 second by 1 by 60, right? So I'm going to write out 20, okay? And instead of second, I'm just going to write my minutes. And instead of 1, I'm going to write 1 over 60, right? So yeah, exactly. And now based on the rules of fraction, what I'm going to do is I'm going to simply do this 20 meters over 1 minute, and I'm going to have to bring this constant over here times 60. So you get 1200 meters per minute. Okay, so this is you've just gone from one set of the units to another set. So in this particular case, what we were asked to do was specifically focus on one of those quantities. That was the time itself. Okay, now let's do something else. Okay, what we're going to do is, if I were to ask you, okay, so if you have, say, the speed is 10 meters per second, and I want that in kilometers per hour. Okay, so now what is being asked of us is to convert the units for both the distance and the time. Okay, so here's the thing. So the original speed is 10 meters per 1 second. Okay, and now what we have to first of all do is Or we can do the same thing. We can first convert time, and then we can convert, for example, the distance. Or we've already seen how time is converted, so let's look at distance. Okay. So in the same way, what we want to do is we want to convert this unit, this meters, into minutes. So let's look at this. Okay. We know that 1 kilometer is equal to 1,000 meters. Okay. And so what we do is, here's the thing. Yeah, exactly. Because what we want to do is we want to convert this 1 meter into kilometers. So we divide both of these sides with 1,000. Okay. And what we get is, this implies that 1 meter is actually 1,000th of a kilometer. Okay. So this tells us that 10 times 1/1,000 kilometers. And then, let's look at how the seconds are converted into, the hours. Okay. So 1 hour is equal to 60 times 60 seconds. Okay. And so if we divide, 60 times 60 on both sides, that is how we get, this entity. So over here, we are going to get 1/3600 hour. Okay, so now this is the final form of our conversion. Okay, now as you see that the units are correct. Okay, all now that we're supposed to do is manipulate these fractions. But as far as the units are concerned, now we're getting kilometers. We're getting kilometers in the numerator and an hour in the denominator. Okay, so let's just do that very quickly. So 10 times, say, 1,000, okay, over 1/3600, okay, and so this is kilometers per hour. And then what we do is, what we get is 10 times 3,600 over 1,000. And so if we cancel out all the zeros, our final answer is 36 kilometers per hour. Is it 36 or 3.6? Okay. Should be 36, no? Can you recheck? Is it 36 or 3.6? All right. Okay. So yeah, be very careful in when you are, kind of, canceling out these zeros, because, you know, that kind of messes up if you make a mistake over there. Okay, great. So moving on. Okay, so here's a slightly different take on the rates itself. Okay, over here you're given the rate. Okay, and from what we discussed in the first slide, you can find out the time. So basically what we have is, because rate is equal to quantity over time, so this implies that if we're supposed to find out the time, what we do is we divide the quantity by rate. Without going into the details, what is the quantity over here? Let's take a look at this statement. A bus travels at 50 miles per hour. How much time in hours will it take to cover 180 miles? So what is the quantity that is being discussed over here? The quantity is this distance, which is 118 miles. Okay. What is the rate that is being discussed over here? The rate is the speed of the bus that is traveling. Okay. So if we were supposed to find out the time, all we need to do is we have to take the quantity, which is 180 miles. Okay. And again, divide this by 50 miles per hour. Why I keep on writing these units is, again, because this is going to come in very handy. Let's forget about this for a moment, and let's just, focus on these units: miles times miles per hour. Okay, I'm just going to write it down over here: miles over miles per hour. Okay, because these are fractions. Okay, so if we simplify this fraction, you get miles over miles times hour. Okay, so the miles are going to cancel each other out, and you're going to be left with hour. Okay, which is what is being asked of us. Okay, so this is why it is very important that you keep a note of the units that are being involved. So that is due to both reasons. So you can verify your answers. And secondly, it can also help you, in identifying, especially in cases whether there is a unit conversion involved. So for example, if I were, to change this question and tell you, or maybe ask you that how much time in minutes is it going to take for the bus to cover 80 miles an hour? So there are two ways. Either I convert the speed into miles per minute, or the second way is I can find out the total time in hours which the bus is going to take to cover 180 miles, and then convert that time into minutes. Both of them are going to mean the same thing. Okay, so in this particular case, yes, I see that a lot of you have really grasped this really quickly, and work your way through the example really quickly. That's wonderful, really. And so the time that we find is that if we divide 180 by 50, you get the answer, which is 3.6 over here. Okay, and so remember, the units are in hours because that is where or that is the units in which the question asks us to provide the answer. Okay, so one more thing that I want to, kind of cover, before, for example, we move on, is that it's essentially very important that knowing whether the conversion is linear or is this, because of a suffix or prefix. And you're going to face these challenges a lot, particularly when you're going, let's say, from meter squared to kilometer squared. So specifically in cases of area, or where the units are actually squares or cubes, going from cubic meters to liters, or for example, in such cases, it is essentially very important that you understand what you're supposed to do. So for example, I'm just going to give you, this is a quick detract, but I wanted to make sure that you understand the significance first. So here, what we have to do is, for example, we know that 1 kilometer is equal to, 1,000 meters. Okay, 1 kilometer is equal to 1,000 meters. Okay, so 1 kilometer squared would mean that now you have 1 kilometer times 1 kilometer. Again, because rules of exponent, we're going to cover them later. But here's a quick thing: is that you've got the same base over here. So if the bases are the same, what you can do is you can add up the powers. Okay, so simply that means that a kilometer times a kilometer means a kilometer squared. Okay, and this means that now once we convert them into meters, so 1 kilometer means 1,000 meters times this kilometer also means 1,000 meters. So effectively, what 1 kilometer square represents is 1,000,000 square meters. Okay, so please, when you are converting units, okay, please make sure that the conversion is accurate. So we're going to cover this later, but I wanted to make sure that you understand why taking the units along, especially in word problems, can be really crucial at times. Okay, so let's quickly get back to our own slide. Okay, so I hope that the significance of the units and how to tackle, the basic quantities between rates, the quantity, and time is evident, and how we are supposed to tackle that. Okay, let's do one more questions. Okay, in this particular case, in one of the scenarios that we've discussed in one of the earlier slides, is that what happens if there are two different rates provided to you, and you're supposed to find the answer in a relative term, or if they're contributing to a same goal. How does that change things? So this is one example of that scenario. So that Now you have two trains starting together. One is at 40 miles per hour and the other is at 60 miles per hour. Okay. How long until the faster train is 50 miles ahead? Okay. Now, there are ways to do that. Okay, there are ways to do that. Back solving is one of them. Effectively, what you can do is you can start off this with back solving instead of jumping into finding or identifying the rates. What you can do is directly go for back solving. And let's do that for this particular example. Let's take the middle, option first. Let's say we assume that the answer is 2.5 hours. What does that mean? That means that we are assuming, okay, so that means that the train that is traveling at 40 miles per hour, okay, in 2.5 hours, how much is it going to travel? So the total distance is going to be the total speed times time. Okay, how did I get over there? I got over here by this basic formulation. Okay, rate is equal to quantity over time. And now I'm supposed to find out the quantity, so I multiply the rate with time. So over here, the rate is your speed, okay? So I'm assuming that this happened, whatever this condition is, this happened in 2.5 hours, okay? So I'm going to first of all multiply what is the distance, or what is the distance that has been traveled by this train at 40 miles per hour, okay? So 40 times 2.5 is 100. So because this is supposed to be the distance, so this is 100 miles, okay? And now, so the first train in 2.5 hours is going to travel 100 miles. And now let's look at what the second train is then. And with the second train, if we do the same thing, so if we multiply the second train's speed with this time, we get 150 miles, right? And so how long until the faster train is 50 miles ahead? Now we've seen that within this window, this time window, which is 2.5 hours, the faster train has already traveled 150 miles, while the slower train is at 100 miles. And so now the difference between whatever they have traveled is a 50 miles. So this is your correct answer. So instead of jumping into, for example, the rates or trying to calculate, doing this in a reverse order, that would have taken us a lot longer. So for example, I would have assumed, for example, let's say to start with, I'm going to say that, okay, in 1 hour, the slower train travels 40. And so in 1 hour, the faster train travels 60. Okay, so the distance is 20 miles. Okay, I'm going to, jump ahead. What happens at 1.5 hours? Okay, so at 1.5 hours, the slower train, this train travels how much? This is going to travel 60 miles. And so this faster train is going to travel 90 miles. So now the difference is 30 miles. So I have to keep on going. But with back solving, I can do this rather quickly. So for example, instead over here, I keep on, coming back to this particular aspect. So over here, if the total time was, let's say the option C represented 4 hours. So what would have happened was I would have multiplied 40 by 4, which is 160, okay, and 60 by 4, which is 240. And so now I can look at this in this way, that I can say that at 4 hours, the distance between these two trains is already 80 miles, okay? So instead of jumping maybe to a higher time, I would have taken a step back and gone towards a shorter time. I would have probably gone to 3 hours or 2.5 hours, whichever is the next lower option. Okay. So I keep on telling you this is that this, back solving works. And not just, you're not doing this randomly, you're not picking up the answers randomly. You start at one point, which is, for example, the middle. Why do we do that in the middle? Because GRE provides the answers in an ascending order. Okay. And so if your answer is exceeding the limit, you take a step back. Or if your answer, whatever you've arrived at, is falling short of your requirement, then you take a step back. Okay. So this is not just random. This is what back solving tells you. And this is possible because GRE provides the answers in an ascending structure. Okay, right. Moving on. Okay. So this is an interesting question. Okay. Now you've got two workers, but there is no quantity. Okay. Worker A can finish a job in 10 hours. Okay. Worker B can finish a job in 15 hours. Okay. Now you put both of these workers on the same thing. Okay. You ask both of these workers to complete or finish the same thing. And the question asks that if they were supposed to work together, or if they were made to work together, how long will it take for them to finish the job? Okay. Now here's the important thing. The important thing is, over here we are just given this time. Okay. Uh, that's great. That's wonderful. Okay, but let me still do that for the other participants as well. So we're just given this time. All right, we're given this time for worker A, and we're given this time for worker B. Okay, and so let's assume that the total task or your quantity is X. All right. Okay. So in case of worker B, what is the rate with which worker A works? Okay. Your worker A works at a rate of X by 10. Okay. Because this is the total quantity and this is the total time. Right. What is the rate with which worker B works? Worker B works with a rate of X by 15. Okay. And so now if I go back to the definition of my rate, what is the definition of rate? The definition of rate is quantity over time. Okay. So this is my quantity and this is my time. All right. And if I simply add these rates together, okay, what I'm going to do is I'm going to simply add these rates together. I'm going to say, okay, the total rate is going to be X over 10 plus X over 15. All right, so that is my total rate. But what the question asks of me is not the rate. The question does not ask me, what is the total rate? Instead, it asks me how long. So instead, it is asking me to find time. Okay. And so how do we do that? How would we do that? Can somebody quickly think based on, what we have already, discussed in our earlier session, in our earlier slides? Okay. So here's the thing. If I say something like this, so this is X by 10, right? So this is my rate. I'm just going to write this very quickly. So my rate is equal to quantity over time, okay? And because I'm supposed to find time, okay, I'm supposed to find time over here. What do I do is I say that this implies that time is equal to quantity over rate, okay? So here's the thing. I do something like this. This is my total rate. Let's figure this out first, okay? Let's take X as common, and I say, this is my total rate with which they are working, okay? And I keep on doing this. I'm not sure what is going to come on the right side, okay? Right, okay, that's great. So now let's solve this first. Let's forget about this part first, okay? And let's solve this first, okay? What is if I'm going to try to solve this, what is, for example, my answer going to be? So over here, let's take the LCM, which is going to be 30, okay? So now I have 3 over here plus 2 over here. So let me quickly erase this part, okay? Going to bring this up really quickly, okay? And so over here we have 30. So this is 3 and this is 2. I've taken the x as common. And so what I get is, 5 over 30, right? Something on the right side as well, okay? And then, so this is my total rate. This is my total rate, okay? Total rate. So total rate is equal to this, okay? And so over here, what I do is I say that my total rate is equal to, I'm going to look at this, 5 over 30. And so my total rate is equal to x times over 6. Okay, so this is my total rate. And what does this quantity represent over here? In the rate, in my definition of rate over here, what does this quantity in the denominator represent? This represents your total time, okay? Because this quantity does not change, and this was my total task. This was the total task that I was supposed to do. So this remains x, okay? And what does this represent in the denominator? That is the total time that it takes for me if, for example, workers A or B, they were working together, okay? So this is, when when I've added these rates, my total rate has come out to be my total quantity, which is x. I don't know what that quantity is over the total time that is going to take for me, okay? And so this quantity is what my answer is, because I was supposed to find out how long. I'm not really sure about the volume of the work, but I do know that the volume of the work does not change. For A, it was x. For B, it was x. And now when both of them are working together, then the volume of work does not change. Okay. And this is what tells me that this is the total rate. And so this total rate is important again. If, for example, my total rate somehow or the other, okay, came out as 3x over, let's say, 15, what would that mean? That would actually represent something different, okay? I'm just slightly, taking you on to how to interpret the rates themselves. This tells me that the total quantity or the total volume of work is actually tripled, okay? And now, so this rate is not the total volume. This time is not the time that it takes for me to complete X, but this is the time that it takes for me to complete 3 times that of the X, okay? So this is important, that where we understand the concept the concept of rates is that why I was simply able to say that this is the total time was because the total volume hasn't changed. If this was, for example, 7x over 18, that would mean that this is the time. If was my total rate, that would actually mean that this is the time that it took workers A and B to complete 7 times their original task, okay? But in our answer, when we multiplied these rates together, what we got was the original volume, or the original quantity of work in its original form. X does not change. And that is why we can say that, yes, if both of them were supposed to work together, the total time that's going to take for them is 6 minutes. If, for example, there was a situation where I had gotten this answer, okay, so simply by simplification rules, I would say that, okay, now that with the total quantity that I'm supposed to complete, and now then, the total time that we get is 3, okay? So over here, in terms of rates, it is important to consider, what is your time being, compared against. So over here, when we, compared both rates with the total rate, what we got was x over 6. And this told us that this, again, because this is the total quantity of work that we're supposed to do, this is this. The other way of doing this, which is very, kind of direct and does not involve this x, is that we simply say that, okay, this is the last thing that we're going to do today. So in that particular case, what we do is that we say that, okay, if this worker, works 10 hours and completes the task in 10 hours, so it's going to do a single unit in, 1/10 of that time. And similarly, what this worker is going to do is, doing that, the basic is going to be like, 1/1/15. Okay, so this is kind of dividing them into the smallest fraction. Okay, or what is the smallest fraction? So this is, if this is the total time for worker A, I'm going to do that, say, in 10. And so this is going to be the time that, worker A consumes, or this is the smallest entity of time that it takes for worker A. And for worker B, it's going to be slightly different. And so because these are 15 in total, these should be 15 in total. So this represents, 1/15, the kind of rate. And what is the rate? So over here, we're getting, 1/10 for worker A, and worker B is 1/15. Okay. If this was, sorry, this should be over here because the volume of work is the same, only the gradients are changing. Yeah, exactly. So what you're getting is, this is the smallest unit of work that is being done by worker A, the smallest unit of work that is being done by worker B. Or more similarly, you say that this is 1/, as one of your friends has, very rightly mentioned. Okay, why? Because your rate is equal to quantity over time. Okay, and so what we do is we say that instead of this entire quantity, we say that what is it's going to take, for a fraction of this quantity to be worked. Okay, if the total was, X, and worker A was doing that in 10 hours, so this is 1/10. All right, and so for worker B, the same is going to have, 15 different units, and one, unit is going to be 1/15. So your total time in this particular case, you can find this out in a slightly different manner, is that you can say that the reciprocal of the total time is going to be the reciprocal of, for example, the time taken by the first entity, okay, and the reciprocal of the time taken by the second entity. This is another way of doing these rate problems where the total volume or the quantity of work isn't provided to you. Okay, so in this particular case, the total, thank you, Mudassir, uh, for sharing this. So this is another way of doing that. Okay, so instead, when you're not given the total volume of work, you can use this way. So what this means is that the reciprocal of the total time, when you've got more than one workers or more than one rates involved, so the total, the reciprocal of the total time is going to take more than one entities, is going to be equal to the reciprocal of the times taken by the individuals. Okay, why is it different? Is because, for example, if I would do simply, if you would do simply like something like this, that would give you a wrong result. Why? Because if I do something like this, that would actually mean that if I am joining workers A and B, now they're going to be taking 25 hours. Okay, instead, what is actually happening is, because I am joining workers A and B, the time should be less. And so what this tells us is that, for any task, when the rates are being merged, the total time, or the reciprocal of the total time, now, taken in the presence of more than one workers, is equal to the reciprocals of the total time taken by them individually. Okay, and this particular expression is, uh, really kind of helps you, particularly in scenarios where the total volume or the total quantity is given to you, and you're just given, for example, some semblance of time or rates. Okay, specifically in this particular case, you're given times only. So how you go from times to rates is that you simply, instead of focusing on the rate, one way was that what we did was we assumed the total quantity, we arrived at the same result. This is a simpler way. Yeah, you can say that. You can also say that it is a reciprocal because, with respect to time, yes, as I said, because if we were doing something like this, okay, x over t1 plus x over t2. Okay, so here's the thing. This is what we actually mean. Why this actually comes over here is, thank you for that. Let me just quickly clarify this last thing before we, call it off. Okay, so this is the total time. This is the total quantity over the total new time. Okay, and this is, the total volume over the total time taken by worker one, and this is the total volume, divided by the total time taken by worker two. And now you see where I'm heading with this. You arrive exactly at what we were discussing earlier. So this is kind of a simplified form. So this is a longer way of doing this, where you first have to assume x, and then you come over here, then you simplify, but you end up at the same point. So in the previous way as well, the first way that we did, that was perhaps a longer way, but that was, provides you kind of understanding of how rates are supposed to be dealt with. This is a shorter and more direct way. So, and this is, also mathematically correct. So as we've just seen that, this can be derived from, the overall scheme of things that we have just discussed in the rates and quantities over time. Okay. So what is important for you to consider is that this is actually extracted from this. Okay, because the volume is common on both sides, so it kind of effectively cancels on both sides. So now you're left with the reciprocal of total time is equal to the sum of the reciprocal of all the contributing times. Okay, so I hope that this has been, a good session. Just before leaving you, let me just quickly clear this up for you. If you're given, quantities, or if you're given, contributing factors, and you're not giving rates, you're not giving quantities, but you're just given times. So in that particular case, remember this, that the total time it takes in this particular case is equal to the sum of the reciprocal of the contributing, entities. Okay, and we have just seen how we arrived at that. Okay, so with this, we come to the end of this session. I hope that this has added value. Again, it has made rates, easier for you to understand, and I hope that you're going to continue working well, and this is going to come in really handy for you whenever you are planning to appear for your GRE exams. Okay, so with this, we're just going to be starting with another session for our